Alright, welcome back. Hopefully you guys can see all this. This is angle 1 and angle 2 on here, little 1 and 2 there, just to save you some writing. I'm hoping you tried this proof already. Hoping you had a few minutes to try this. Sorry for that last video being kind of short. I had to go to a meeting, so I broke out of the meeting. Now I'm back. The whole reason I gave you this, that ST bisects angle MSN, I don't want you to jump to false conclusions. A lot of people will say, well, if this ST is bisecting angle MSN, then these sides are congruent, or these angles are congruent, or these angles are congruent, or these sides are congruent, or the conclusions just come out of nowhere. There's only one quick conclusion. If this is bisecting MSN, it means these two parts of the angles are congruent. So hopefully that's the conclusion you got to. 1 congruent to 2. And if you didn't include this right here, you still need that. So somewhere in there in the proof, you have to recognize that 1 and 2 are congruent. Because you understand that that word means cut into 2 equal parts. Cut specifically that angle into 2 equal parts. 2 congruent parts. So, with that one piece of information, you can prove that 2 triangles are congruent. If you look at which one SRM is the top triangle on the left, and you can prove that's congruent to the bottom triangle on the right, or on the left, sorry, SRN. With those 2 angles, and the side that's here, plus the shared side, which I'm not going to include in the actual proof, I'll put some marks on it here to help it make it more obvious. It's pretty obvious this should be side, angle, side, congruent to side, angle, and a side. And if I were to flip this down, it would be a reflection onto itself. So I've got side, angle, side by reflection. Now, this is where I want to just talk about it for a second. I can prove the triangles on the left are congruent, just with some given stuff. The triangles on the right, there's not enough information. I've got a side and I got a side. I've got a shared side. But you don't know anything about these 2 angles in the beginning. You don't know anything about these 2 angles. And in the beginning, you don't know anything about these 2 sides. However, we just proved these triangles are congruent. So obviously this side is congruent to that side. So now you have all 3 sides. The shared side, the cpctc side that we're stealing from this triangle, cpctc side we're stealing from this triangle, and the given sides on there. So now we can say RM congruent to RN, and finish it off with a cpctc step. And then you can prove that triangle RMT, the top right triangle, is congruent to the bottom right triangle. If I say RMT, I should be saying RNT. And of course we just said it, there's one pair of sides, shared side, and the cpctc sides we just stole from the other ones. You have side, side, side also by a fold or a reflection. And now, what we're trying to prove here is that the angles are congruent. RTM is this angle. It's congruent to RTN. Now, some of you, in the very beginning when you read this, you may have made an assumption that everything got bisected on there. Well, we did just prove that this angle got bisected as well at the end here, because these parts, these 2 angles, are parts of these 2 triangles. So another corresponding parts of the congruent triangles we just proved were congruent. So I don't know if those are the easier proofs or the harder proofs. Not quite sure. Give you one more on this little video segment. Hopefully you guys can hear me. I don't have a microphone today. Sorry about that. So I'll flip the page over. On example 4 on the back, the given is that you got a bunch of congruent angles. You can add this in as a given on your paper. A is the vertex at the top, B and T are the corners, M and N are the corners of this small triangle on the inside there. And of course you're probably saying, where are 3, 4, and 5? Or sorry, 1, 2, 3, and 4. Angle 2 is here. Angle 1 is right across from it. And you're actually probably going to use angles 5 and 6 in this proof somewhere. So I'm just trying to save you a little bit of writing by including angles 5 and 6 on there. This is a good one to pause. And you'll see on your paper I labeled it as 5 steps. I'm hoping you might be able to either work forwards or backwards. There's 2 big steps that nobody in 5th or 6th period was really comfortable with, and even nobody in the last period, 7, 8, was really comfortable with, because there's 2 things they haven't really remembered. 2 theorems we haven't used very often, or often enough. Part of the reason I picked them on this, just to refresh your brains about them. So again, you might want to pause, see what type of logic you can piece together for these steps that are missing in here. And obviously this whole chapter is about proving triangles are congruent. Where and here can you prove triangles are congruent, or how can you prove triangles are congruent? I hope you get to the point where you go, well, this isn't enough. I have a pair of angles and a pair of angles. You have to have a side. You can't prove triangles are congruent without a side. But I did kind of give you a side when I gave you this. If 1 and 2 are congruent, think about which sides are congruent. And hopefully you come up with MA congruent to NA. And it's because the angles are congruent that these are congruent. Now, most people in the other classes, like the vast majority, maybe 90% of people in the other classes, didn't remember the name of this theorem. And I've asked a couple of people, how would you explain that in your own words? Because if you don't remember the name of the theorem here on the test, you're going to write a sentence or two explaining why these sides are congruent. So think about how you do that. You might say, well, if 2 angles of a triangle are congruent, then 2 sides of a triangle are congruent. Or if 2 angles in a triangle are congruent, then the sides opposite of them, opposite of 2 and opposite of 1, the sides opposite them are also congruent. You might say if a triangle has 2 angles that are congruent, then it is isosceles, and therefore has 2 congruent sides. It's called the isosceles triangle converse, not the theorem. It's the converse of the theorem. And if you go, oh, what's the difference between the theorem and the converse? Well, the converse is when you don't know it's isosceles. Converse is when you know 2 angles, and then you draw the conclusion that the sides are congruent. The isosceles triangle theorem is where you know 2 sides. It would be the other way. If you know 2 sides are congruent, you conclude the angles are congruent. Almost the same thing, just the logic of them is a little different. One you're given angles, one you're given sides. So now we've got, and it doesn't even show up in your paper, but there is a little segment mark over both of these. Should be segment marks over both of those because we're talking about congruence. We have a pair of sides, and you have a pair of angles. And it might be obvious you're maybe going to go after these 2 triangles to be congruent, because at the end of this we're trying to prove BM, this little piece, is congruent to TN, which these 2 are parts of the white triangles on the sides. So if there's some way, you have a pair of sides, you have a pair of angles, if you get maybe another angle or another side on there, most people pretty logically could see that 5 and 6 would be congruent. This is a hard one to remember. The name of the theorem is hard to remember. And you'd probably explain this in your own words on a test. You'd say, well, 5 and 6 are congruent because they're supplements to the exact same angle, or they're supplements to congruent angles. 1 and 2 are congruent. So if this was 80, this would have to be 100. If this was 80, this is also 80, and that would have to be 100. So 100 would equal 100. It's called the congruent supplements theorem. Look back at chapter 2 in your notes a couple chapters ago. We haven't used this a lot. That's the theorem we're referring to. In other words, these 2 angles, 5 and 6, are congruent because they are supplementary to a pair of congruent angles, or supplementary to the exact same angle. And the last thing is the big one. Prove that triangle BAM is congruent to triangle TAN. So BAM, TAN, and of course you can do that just looking at the drawing. You've got an angle, a side and an angle, congruent to an angle, a side and an angle, and it would be by a flip or a reflection. And the last step better be obvious now. BM congruent to TN, because we just proved that the triangles are congruent, therefore their parts, those bottom sides, are also congruent. So hopefully you're feeling like a cpctc expert. I'll give you some letters on this last one to work on, and we'll finish number 6 in class. Hopefully you have a chance to try this one. Trying to prove this little triangle, LIT, is isosceles. You'll have to change this on your paper. On your paper this is a T. Change it to RA. That's a typo mistake on there. The other letters you're going to need, this is triangle BIG, this bigger triangle here, triangle BIG. And the other triangle that's fairly large is triangle LAR. So 3 triangles you're going to compare in this one. This thing can be done, like it says in your paper, in 4 steps. Do not state the givens in your 4 steps. So 4 logical steps. I'm going to pause this thing and go on, record on the next part, or I'll talk about it tomorrow in class. Hopefully you come in with this thing done, because you're an expert now.